Welcome back. This is the first video in our long series on the implementation of compilers. Recall from last time that a compiler has 5 phases. We're going to begin by talking about lexical analysis, and this will probably take us 3 or 4 videos to get through at least, and then we'll be moving on in order to the other phases. Let's start by looking at a small code fragment. The goal of lexical analysis is to divide this piece of code up into its lexical units. So things like the keyword if, the variable names I and j, and the relational operator double equals, and so on. Now, as a human being, this is as we discussed last time, this is a very easy thing to do because there's all kinds of visual clues about where the units lie, where the boundaries between the different units lie. But a program, a lexical analyzer, doesn't have that kind of luxury. In fact, what the lexical analyzer will see is something that looks more like this. So here I've written the code out just as a string with all the white space symbols included. And it's from this representation, just as a linear string, you can think of this as bytes in a file, that the lexical analyzer has to work. And it's going to march through placing dividers between the different units. So it'll recognize that there's a division there between the white space and the keyword, then a division after the keyword, and some more white space, the open paren, the I, another white space, double equals, and so on. And it goes through drawing these lines, dividing up the string into its lexical units. And I won't finish the whole thing, but you should get the idea. Now, it doesn't just place these dividers in the string, however. It doesn't just recognize these substrings. It also needs to classify the different elements of the string according to their role. And we call these token classes, or sometimes I'll just call it the class of the token. And in English, these roles are things like noun, verb, adjective. Okay, and there are many more, or at least there are some more. And in a programming language, the classes, the token classes would be things like identifiers, keywords, and then individual pieces of syntax like an open paren or a closed paren. Those would be classes by themselves. Numbers. And again, there are more classes, but there's a fixed set of classes, and each one of these corresponds to some set of strings that could appear in a program. So token classes correspond to sets of strings, and these sets of strings can be described relatively straightforwardly. So for example, the token class of identifiers in most programming languages might be something like strings of letters or digits starting with a letter. So for example, a variable name or an identifier could be something like A1, or it could be foo, or it could be B17. All of those would be valid identifiers. And often there'll be additional characters that are allowed in identifiers, but that's the basic idea. Very, very often, the main restriction identifier is that they have to start with a letter. An integer, then, typical definition of an integer is a non-empty string of digits. So something like 0 or 12, okay, 1 followed by 2, I should say, is actually a string, not a number in this case. And you know, this actually would admit some numbers you might not think of. Things like 001 would be a valid representation of a number, or even 00 could be a valid integer according to this definition. Keywords are typically just a fixed set of reserved words, and so here I've listed a few: else, if, begin, and so on. And then white space is itself a token class. So we actually have to say in that string, which is the representation of the program, what every character in that string, what token or what token class it's a part of, what every substring is a part of, and that includes the white space. So for example, if we have a series of 3 blanks, if I say if and then an open paren and I have 3 blanks in here, these 3 blanks would be grouped together as white space. So the goal of lexical analysis is to classify substrings of the program according to their role. This is the token class. Okay, is it a keyword, a variable, an identifier? And then to communicate these tokens to the parser. So drawing a picture here, let's switch colors. The lexical analyzer communicates with the parser. Okay, and the functionality here is that the lexical analyzer takes in a string, typically stored in a file, so just a sequence of bytes, and then what it sends to the parser is a sequence of pairs, which are the token class and substring, which I'll just say string here, which is so it sends a string which is a part of the input along with the class, the role that it plays in the language, and this pair together is called a token. All right, and so for example, if my string is that foo equals 42, all right, then that will go through the lexical analyzer and out will come, I'll write it down here, 3 tokens, and these would be identifier, foo, operator, say, equals, and integer, 42. And here I've just left these things as strings to emphasize that these are strings. So this is not the number 42 at this point in time. It's the string 42, which is plays an integer role in the programming language. And then what the parser takes as input is this sequence of pairs. So the lexical analyzer essentially runs over the input string and chunks it up into this sequence of pairs where each pair is a token class and a substring of the original input. Let's return to the example from the beginning of the video. Here it is written out as a string. And our goal now is to lexically analyze this fragment of code. We want to go through and identify the substrings that are tokens and also their token classes. So to do this, we're going to need some token classes. So let's give ourselves some of those to work with. We'll need white space. And so this is sequences of blanks, new lines, tabs, things like that. We'll need keywords. Okay. And we'll need variables, which we'll call identifiers. And we'll need integers, and I'll call those numbers here. And then we're going to have some other operations, some other classes, things like open paren, close paren, and semicolon. And these are interesting. These 3 are interesting because they're single character token classes. That is, it's a set of strings, but there's only one string in the set. So the open paren corresponds to exactly the set of strings that contain only open paren. So often the punctuation marks of the language are in token classes all by themselves. Another piece of punctuation that we'll add here is assignment. That'll be in a token class by itself because it's such an important operation. But the double equals will class as a relational operator. We'll just class it as an operator, put it up here. All right, so now what we're going to do is we're going to go through and tokenize this string, and I'm going to write down for each substring what class it is in, and I'm just going to use the first letter here of the class to indicate it, just to save time so I don't have to write everything out. And let me change colors so we can do this in a different color. So the first token here is a white space token, and that followed by the if keyword, so K. And then we have a blank here, which is another white space. And then the open paren, which is its own token class, so I'll just leave it to identify itself there. And then we have an identifier, okay, white space, and then an operator, the double equals. another blank, so that's white space, followed by another identifier, followed by close paren. So again, a punctuation mark in a token class by itself. And then we have 3 white space characters, so those are grouped together as a white space token, followed by another identifier and more white space, and then another single character token, the assignment operator, white space, and a number. All right, and then semicolon again, a punctuation mark in a token class by itself. 2 white space characters get grouped together. What follows then is a keyword, so that gets classified as in the keyword token class. Another run of white space characters, and then another identifier. There's actually a blank there, although we almost covered it up with our marks. The assignment operator by itself in a token class, white space, a number, and finally the semicolon by itself. And there is our tokenization. We've identified the substrings, and we've also labeled each one with its token class. To summarize, lexical analysis implementation has to do 2 things. The first job is to recognize the substrings in the input that correspond to tokens. And here's a little bit of compiler lingo. These substrings are called the lexemes. So the words of the program are called the lexemes. And then the second job is that for each lexeme, we have to identify its token class. And then the output of the lexical analyzer is a series of pairs, which are the token class and lexeme. Okay, and this whole thing, one of these pairs, is called a token. Welcome back. In this video, we're going to continue our lecture on lexical analysis with some examples from past programming languages where interesting lexical problems arose. So we've already talked a little bit about Fortran, and one of the interesting lexical rules in Fortran is that white space is insignificant. So white space doesn't matter, and something like var1, which could be a variable name var1, is exactly the same as va space r1. So these 2 program fragments have to mean exactly the same thing. And the idea in Fortran is that you could take your program and you could delete all the blanks from it, and that shouldn't change what the program means at all. Let's take a look at an example of how Fortran's whitespace rule affects lexical analysis. Here are a couple of Fortran code fragments, and I should say that this example is taken from the Dragon book, and actually a couple of the later examples are also taken from an older edition of the Dragon book. But anyway, what we have here, this is actually the header of a Fortran loop. And you know it's a loop because it has the keyword do, which is like for in modern C or C++. So that's a loop keyword. And then we have our iteration variable I, and we have a range that I will vary between. So in this case, I will go from 1 up to 25. And then this number 5 here, this is a little bit odd and something you don't see in modern languages. In the old days, in Fortran, you would have your do statement at the top of the loop, and then the size of the loop, or all the statements included in the loop, were named by a label that came right after the do statement. So the loop would extend from the header, the do statement, down to the label 5. So whatever statement was labeled with 5, all the statements in between would be part of the loop. And so the loop would execute those statements, then would go back around to the header, and it would keep executing those until it had done so for every one of the values of the iteration variable, in this case 1 to 25. Now here's another code fragment, and as you can see, this one is almost exactly the same as the one above. The only difference is, and let me switch colors, is here that this particular fragment has a comma in that position, and this fragment has a period. And it turns out that this difference makes all the difference, that these 2 fragments of code mean completely different things. So this fragment the first one, is in fact a do loop, as I said before. So it has the keyword do, the label 5, the variable I, and the range 1 to 25. Now this fragment down here, this is actually a variable name, do5i. So if I was to write it without the blanks, remember the blanks don't matter, this would be do5i, and then this is an assignment equals the number 1.25. Okay? And so you can see here, these symbols, this first sequence of symbols is interpreted completely differently depending on whether there's a period or a comma further on. And so let's just be a little more precise about that. How do we know what do is? So let's just focus on the keyword here, do. And when we're at this point, when our focus is here, right after the O, and keep in mind that that the way this is going to be implemented is by a left to right scan. So we're going to be walking in this direction over the input, looking at each character successfully. And when our focus reaches this point, we can make a decision. Is this a keyword? Because we've seen the entire keyword do. And the problem is that we don't have enough information to make that decision. We don't know whether this is do or whether it's going to eventually be part of a variable name like do5i. And the only way to know is to look ahead in the input to this position to see whether there's a comma or a period there. So this is an example of lexical analysis that requires look ahead. In order to understand the role of do, as we're going left to right, we have to peek ahead in the input to see some symbols that come later on. And we can't possibly disambiguate the role of do until that point, because up to this point, the sequences of symbols are exactly the same. And so the only thing that distinguishes them is something that's much, much further on. And as you can imagine, having lots of look ahead complicates the implementation of lexical analysis. And so one of the goals in the design of lexical systems is to minimize the amount of look ahead or bound the amount of look ahead that is required. So you might wonder why Fortran has this funny rule about white space. It turns out that on punch card machines it was easy to add extra blanks by accident, and as a result they added this rule to the language so that punch card operators wouldn't have to redo their work all the time. Fortunately today we don't enter our programs anymore on punch cards. But this example does help us understand better what we're trying to do in lexical analysis. So as I said, the goal is to partition the string. We're trying to divide the string up into the logical units of the language. And this is implemented by reading left to right. So we're doing a left to right scan over the input, recognizing one token at a time. And because of that, look ahead may be required to decide where one token ends and the next token begins. And again, I want to stress that look ahead is always needed, but we would like to minimize the amount of look ahead. And in fact, we'd like to bound it to some constant because that will simplify the implementation of Lexical Analyzer quite a bit. Now, just to illustrate that look ahead is something that we always have to worry about, let's consider this example, which we've looked at before, and just notice that when we're reading left to right, let's look at this keyword else here, when we've read the E, we have to decide, is that a variable name or some symbol by itself, or do we want to consider it together with the symbols that follow it? And so there's a look ahead issue here. After we've scanned E, we have to decide, does that sit by itself or is it part of a larger lexical unit? And there are single character variable names in this example, like I, J, and Z. And so it's not unreasonable that E could also be one. And another example is this double equals. When we've read a single equal sign, how do we decide whether that's a single equals like these other assignments, or that it's really a double equals? Well, in order to do that, if our focus point is right here, we have to look ahead and see that there's another equals coming up, and that's how we know, or how we will know, that we want to combine the two into a single symbol instead of considering this equals by itself. Now, another example from a language from long ago, PL1 is an interesting language. It was designed by IBM, and it stands for Programming Language 1. All right, it was designed to be the programming language, at least within IBM, that would be used by everybody. and it's supposed to encompass all the features that any programmer would ever need. And as such, it was supposed to be very, very general and have very few restrictions. And so one of the features of PL1 is that keywords are not reserved. So in PL1, you can use a keyword both as a keyword and also as a variable. So you can use keywords in other roles other than keywords. And that means you can write interesting sentences or interesting programs like this. And let me just read this out loud because it sounds interesting. If else, then equals else, else equals then. And the correct organization here, of course, is that this is a keyword, this is a keyword, and this is a keyword. And the other things, switch colors here, are all variables. These are all variable names. And as you can imagine, this makes lexical analysis somewhat difficult because when we're just scanning left to right, like when we're coming through here, when say we're at this point, how do we decide whether these things are going to be variable names or keywords without seeing what's going on in the rest of the expression? So lexical analysis in PL1 was quite challenging. So here's another example from PL1. Here we have a program fragment. We have the word declare, and then an open paren and a closed paren encompassing a bunch of arguments. I want to point out the balanced parens here, and then just a list of n things inside the parens. And it turns out that depending on the larger context in which this whole expression sits, this could be either a keyword or it could be an array reference. Now, I mean declare here could either be a keyword or it could be the name of an array, and these could be the indices to the array. And as it happens, there is no way, looking at just this much, that we can decide. This fragment is a valid declaration, and it's also a valid array reference. So it would depend on what came next. It might depend on, for example, whether there was an equal sign here, in which case this would be interpreted as an assignment, and declare would be the name of an array. And the interesting thing about this example is that because the number of arguments in here is unbounded, there could be n of them for any n, this requires unbounded look-ahead. Okay, so to implement this properly, as you're scanning left to right, to decide whether declare, again, is a keyword or an array reference, we would have to scan beyond this entire argument list to see what came next. Fortran and PL1 were designed in the 1950s and 1960s, respectively, and those experiences taught us a lot about what not to do in the lexical design of programming languages. So things are a lot better today, but the problems have not gone away completely, and I'll use an example from C++ to illustrate this. So here's an example of C++ template syntax, which you may be familiar with, or you may have seen the similar syntax in Java. And C++ has another operator called stream input. So this operator here reads from an input stream and stores the result in a variable. And the problem is here that there's a conflict with nested templates. So for example, if I have a template operation that looks like this, okay, notice what happens here. So my intention here is to have a nested application of templates, but I wind up with two greater than signs together at the end, and this looks just like the stream operator. And the question is, what should the lexical analyzer do? Should it interpret this as two closed brackets for templates, or should it interpret it as a two greater than signs stuck together as a stream operator? And it turns out that for a very long time, I think most C++ compilers have now fixed this, the C++ compiler in this situation would regard this as a stream operator, and you would get a syntax error. And what do you think the solution was? It turns out that the only fix that you could really do to make this lexically analyze the correct way was to insert a blank. So you would have to write this, and you would have to remember to put the blank in there so that the two greater than signs were not together. And that's kind of ugly that we have to put in white space to fix the lexical analysis of the program. So to summarize, the goal of lexical analysis is to partition the input stream into lexemes. Okay, so we're going to drop down dividing lines in the string to decide where the lexemes lie, and we want to identify the token of each lexeme. And exactly because we're doing a left to right scan, sometimes we have to have look ahead. Sometimes we have to peek ahead in the input stream to figure out what the current string we're looking at, or the current substring we're looking at, what role it plays in the language. In this video, we're going to talk about regular languages, which are used to specify the lexical structure of programming languages. To briefly review, the lexical structure of a programming language is a set of token classes, and each one of the token classes consists of some set of strings. Now, we need a way to specify which set of strings belongs to each token class, and the usual tool for doing that is to use regular languages. So in this video, we're going to present regular languages and define what they are, and then in subsequent videos, we're going to look at some examples of using them in actual programming languages. To define the regular languages, we generally use something called regular expressions. And each regular expression denotes a set. There are two basic regular expressions. If I write the single character C, that's an expression, and what it denotes is a language containing one string, which is the single character C. Okay? That's one basic form. So for any single character, I get a language with a one-string language with and then the only string is that character. Another basic building block of regular languages is the regular expression epsilon, which is the language that contains, again, just a single string, this time the empty string. And one thing that's important to keep in mind is that epsilon is not the empty language. Okay, so this does not correspond to the empty string, the empty set of strings. It is a language that has a single string, namely the empty string. Besides the two base regular expressions, there are three compound regular expressions, and we'll just go through them here in order. The first is A plus B, which corresponds to the union of the languages A and B. So this would be the set A such that A is in the language of big A, little a is in the language of big A, union little b such that B is in the language of little b. So just the union of the two sets of strings. Concatenation is like string concatenation. So if I have two languages A and B, or two regular expressions A and B, then the concatenation of A and B is equal to all the strings little a concatenated with little b, where A is drawn from the language big A and little b is drawn from the language big B. And so this is a cross-product operation. Choose a string from A, choose a string from capital B, and then combine, put them together with a string from A first, and choose these strings in all possible ways, form all possible combined strings, and that's the language A concatenated with B. And finally, there's a kind of looping construct. This is pronounced A star, or it's called the Kleene iteration, or the Kleene closure. And A star is equal to the union for I greater than or equal to 0 of A to the ith power. And what's that mean? Well, A to the ith power is just A concatenated with itself I times. So this is A to the I. And note that because I can be equal to 0, one of the possibilities here is A to the 0, so A concatenated with itself 0 times. And what is that? Well, that's the language epsilon. So that's the language containing the empty string. So the empty string is always an element of A star. To summarize the last couple of slides, the regular expressions over some alphabet sigma are the smallest set of expressions that include the following. So let's define it. So the regular expressions are equal to epsilon is always a regular expression. Or another possibility is the single character C, where C is an element of our alphabet. Okay, so this is important. The regular expressions are defined with respect to some alphabet. So we have to pick a family of characters that will form the base cases of the regular expression. And here, we have one base regular expression for each character in the alphabet. And then we have the compound expression. So another possibility is that a regular expression is the union of two regular expressions. Another one is that it's the concatenation of two regular expressions. And the last one is that it could be the iteration of a regular expression. So these 5 cases are the set of regular expressions over a given alphabet. Now, this syntax here for describing the regular expressions with these vertical bars and these different cases on the right-hand side in this recursive definition of R, if you haven't seen this before, this is called a grammar. And that's not important for this lecture. It's not what this lecture is about, but we'll be talking about grammars when we get to parsing. Next, I'd like to do a few examples of actually building regular languages, writing them out and thinking about what they mean. And as we said, whenever we're talking about a regular language, we first have to say what the alphabet is. And so for these examples, let's just use the alphabet 0 and 1. So these are going to be languages which consist of strings of zeros and ones. And let's start with a very simple example. Let's think about the language 1 star and what language that denotes. So, well, we know the definition of star. If we remember, that was the union over I greater than or equal to 0 of 1 to the I. Okay? And what is that equal to? Well, that's just 1 repeated I times. That's what the concatenation of 1 to the I means. Okay? It means 1 concatenated with itself I times. And so this is going to be the empty string. That's 1 concatenated with itself 0 times, followed by 1, followed by 1, 1, followed by 1 concatenated with itself 3 times, followed by 1 concatenated with itself 4 times, followed by 1 concatenated with itself any number of times. Okay, and so we can see that this is just equal to all strings of ones. All right, now let's do a second example. Let's think about the language 1 plus 0 concatenated with the language 1. Okay? And remember how concatenation works. It's a cross product, so we take every string in the first expression and combine it with every string in the second expression. So this is going to be equal to the strings A, B, where A is drawn from 1 plus 0, and B is drawn from 1. All right, and what can that be? Well, there's 2 choices for A. A could be 1 or 0, and B could be 1. So in fact, this is equal to the set 1, 1, and the strings 1, 1, the set containing the strings 1, 1, and 1, 0. All right? Let's do another example. Well, it's slightly more complex. Let's build up here to having 2 iterations in a union. So we'll have 0 star plus 1 star. And think about what that's equal to. Well, we already know what 1 star is equal to. That's equal to all strings of 1s. And so by analogy, 0 star must be all strings of zeros. And then we take the union of those 2 things. So this is actually really easy to write out. Let's write them out in this notation. So we have 0 to the I for I greater than or equal to 0. Okay, so that's 0 star union with 1 to the I for I greater than or equal to 0. That's the strings of all 1. So there's the set that this expression denotes. And for our last example, let's think about 0 plus 1 now, that iterated. Okay, so we put the star around the union of the 2 individual characters instead of having the star on each character individually and taking the union of the 2 things. So what is this expression equal to? Well, let's work with the definition of star. So we know that this is the union over I greater than or equal to 0 of 0 plus 1 to the I. And what does that look like? Well, that looks like, first of all, there's the empty string, right? And then another string in this language is drawn from 0 plus 1. And sorry, I shouldn't say another string, but another set of strings is from the language 0 plus 1, and then 0 plus 1 concatenated with itself, okay? And in general, it's going to be 0 plus 1 concatenated with itself I times. Okay, well, what does that mean? That means that at every position, if we have a string of length I, at every position we can pick a 0 or a 1 to plug in. And this works for any length string. This is going to be true of strings of every length. And so, in fact, this language is just going to be all strings of zeros and ones. And in fact, what that means is it's the set, if you look back at our alphabet only consists of 0 and 1. And so this is the set of all strings that you can form over the entire alphabet. And that has a special name. When that happens, when you have a regular expression that denotes the set of all strings you can form out of the alphabet, we write that as sigma star. Okay, so just meaning all the strings of the alphabet iterated as many times as you like. One last point I want to make on this before we go on here is that there are actually lots of ways to write each of these different languages. There's not a unique way to write these. So for example, let's just take this language here, the second one that we did, and let me switch colors. Another alternative way to write this, since we know the meaning of it is these two strings, 1, 1 and 1, 0, is I could have written it as 1, 1 plus 1, 0. And that would mean exactly the same thing. These two expressions denote exactly the same set. Similarly with 1 star, I could write this as 1 star plus 1. Because this wouldn't change anything. Adding in the single string 1 wouldn't change anything since 1 is already included in 1 star. This might be kind of a silly way to write that set, but it doesn't matter. It has a meaning, and it means exactly the same thing as 1 star. And the point, again, is that there's more than one way to write down the same set. You can write multiple regular expressions that denote the same set. Well, we've come to the end of this video, and to summarize, we looked at regular expressions, which are used to define regular languages. And the regular expressions are syntax, that's the expression that we write down, and it denotes a set of strings, which is the regular language, and that's the meaning of the regular expression. And there are 5 kinds of regular expressions in the standard definition. There's an expression for the empty string, and that's denoted by epsilon. And then we have all the one-character strings. And then there are 3 compound expressions, ways of building new regular expressions from other regular expressions. And these are union, concatenation, and iteration. Welcome back. In this video, we're going to take a little digression and talk about formal languages. Formal languages play a big role in theoretical computer science, but they're also very important in compilers, because inside of a compiler we typically have several different formal languages that we're manipulating. Regular expressions are one example of a formal language, but it's actually helpful, I think, in understanding regular languages and all the formal languages we'll see later on in later videos to talk about what a formal language is in general. So let's begin with a definition. A formal language has an alphabet, so some set of letters sigma, and then a language over that alphabet is just a set of strings of the characters drawn from the alphabet. So in the case of regular languages, we had certain ways of building up sets of strings of characters, but other kinds of languages would have different sets of strings. And in general, a formal language is just any set of strings over some alphabet. An example of a language that you're familiar with is formed from the alphabet of English characters, and it is just the set of English sentences. Now, this is not quite a formal language in that we might disagree on which strings of English characters are in fact valid English sentences, but one could imagine that we could define some rules that would say that certain strings are English sentences and others aren't, and if we could come to some agreement, this would be a fully formal language. Now, a much more rigorous formal language would be something like the following. We could pick our alphabet to be the ASCII character set, and the language to be the set of all valid C programs. And this is definitely a very well-defined language. This is exactly the set of inputs that C compilers will accept. And the important contrast I want to draw here is that the alphabet is actually interesting. So different formal languages, have very, very different alphabets, and we can't really talk about what the formal language is or what set of strings we're interested in unless we first define that alphabet. Another important concept for many formal languages is a meaning function. Typically, we have one of the strings in our language, and let's call that some expression E. And the expression E by itself is just a piece of syntax. It's a program in some sense, or it represents something else that which is the thing we're actually interested in. And so we have a function L that maps the strings in the language to their meanings. And so, for example, in the case of the regular expressions, this would be a regular expression, and that would be mapped to a set of strings, the regular language that regular expression denotes. And we saw an example where we wrote out the meaning function for regular expressions last time. So let's use regular expressions as an example, and I'm going to first write down the meaning of the regular expressions the way I wrote it down in the last video. So if you recall, we had a regular expression epsilon, and that denoted a set which contained just one string, namely the empty string. And then we had a regular expression C for every character in the alphabet, which also denoted a set containing just one string, namely the single character C. And then we had a bunch of compound expressions. So for example, A plus B, that was equal to the union of the sets A and B. And we had the concatenation, so I could juxtapose A and B, and that was equal to a cross product, where I selected a string from each set in order and concatenated them together. And finally, there was iteration. So I could write A star, and that was the union over I greater than 0 of all the sets A to the I. All right, and the interesting thing about this definition is you can see that we're mapping, over here we have expressions. Okay, let me switch colors here. Over here we have the expressions, and over here we have the sets. But there's something kind of odd about the way this is written, and not quite right, because you can see here where clearly we have an expression, we have a piece of syntax, A plus B, and then somehow on the other side, this A and this B have magically turned into sets that we're taking the union of. And similarly down here, we're choosing an element from this set, but this set is also an expression. And what does it mean? Somehow we're conflating the sets and the expressions. And this is what the meaning function is intended to fix. And this is what or intended to make clear. So what we really want to say is that there's some mapping, that the language L of epsilon is this set. So L maps from expressions into sets of strings. Okay, it's a function that maps one to the other. And if you haven't seen this notation before, this is a standard notation for describing functions. It just says that L is a function from things in the domain, in this domain, to this range. Okay, and similarly, the language of this expression is this set. And it becomes really useful for the compound expressions, because here we say the language of this expression is equal to the language of A union with the language of B. And now you can see the recursion. First, we interpret A and B using L, and we take the union of the result. Okay, so now it's clear what's a set and what's an expression. And similarly here, the language of A concatenated with B, we're going to select elements from the language of these two expressions, and then we're going to form another set from those two sets. And finally, for iteration, the language of A star is equal to the union over the meaning of a bunch of expressions. A to the I is an expression. This is a piece of syntax, and we have to convert it to a set in order to take the union. And so now this is the proper definition of the meaning of regular expressions, where we've made the meaning function L explicit, and we've shown exactly how recursively we apply L to decompose the compound expressions into simpler expressions that we compute the meaning of and then compute the sets from those separate smaller sets. So there are several reasons for using a meaning function. We just saw one of them, which is to make clear what is syntax and what is semantics in our definitions. Some parts of the definition are expressions, and some parts are the meanings or the sets, and using L makes it clear that the arguments to L are the programs or the expressions, and the results are the sets, the outputs are the sets. But there are a couple other reasons for separating syntax and semantics. One is that it allows us to consider notation as a separate issue. That is, if we have syntax and semantics being different, then we can vary the syntax while we keep the semantics the same, and we might discover that some kinds of syntax are better than others for the problems that we're interested in or for the languages that we're interested in. And another reason for separating the two is that because expressions and meanings, because syntax and semantics, are not in one-to-one correspondence. And I actually illustrated this with regular expressions in a previous video, but I want to reiterate here that there are generally many more expressions than there are meanings. So that means there may be multiple ways to write an expression that means the same thing. I'd like to take a moment to illustrate why separating syntax from semantics is beneficial for notation. So everybody's familiar with our number system, so I can write numbers like 0, 1, 42, and 107. And there are very nice algorithms for describing how you add and subtract and multiply such numbers. But there are older systems of notation for numbers, things like the Roman numerals. So I could have the number 1, I could have the number 4, the number 10, and say the number 40, I think is written like that. And an issue with this number system, well, first of all, let me stress that these two have the same meaning. So the meanings of expressions in this language are the integers, and it's exactly the same in this language. So the idea, the meaning of these two systems are just the numbers. But the notation is extremely different. A number written in Roman numerals looks completely different from a number written in Arabic numerals. And the fact is that the Roman numerals are really painful to do addition and subtraction and multiplication in. And in fact, back in ancient times when this was a common system, it was not very well known how to do it, and very few people were actually good at doing arithmetic with this system because the algorithms were kind of complicated. And when we moved to the Arabic system later, it was a big improvement because it was easier for people to learn how to do basic arithmetic with these kinds of numbers. And the only thing that changed between one system and the other was the system of notation. And so notation is extremely important because it governs how you think, and it governs the kinds of things you can say and the sorts of procedures that you will use. So don't underestimate the importance of notation. And this is one reason for separating syntax from semantics, because we can leave the idea of what we're trying to do, the numbers, alone, and play with different ways of representing them, and we might discover that some ways are better than others. The third reason I gave for separating syntax and semantics is that in many interesting languages, multiple expressions, multiple pieces of syntax will have the same semantics. Going back again to regular expressions, let's consider the regular expression 0 star. Now, there are many ways to write this same language, which is the language of all strings of zeros, so strings of zeros of any length. So for example, I could also write that as 0 plus 0 star. Another way to write it is as epsilon plus 0, 0 star. And here you can see that this expression is all the strings of zeros of at least length 1, and then we get the empty string from epsilon. So this is equal to 0 star. And there's just, any combination of these things would also amount to an equivalent language, for example, that one, and so on. So there's actually an unbounded, unlimited number of ways I could write this language, but all of these mean exactly the same thing. And if you think about it, what this means is that in general, if I draw the two domains differently and I think about different expressions over here and different distinct meanings over here, and the function L that maps between them, the function L is many to one. So there are, there are points in this space that where many different expressions or pieces of syntax map to the same meaning. And this is just a general characteristic of interesting formal languages. And this is actually extremely important in compilers because this is the basis of optimization. The fact that there are many different programs that are actually functionally equivalent, that's what allows us to substitute one program that runs faster than another. That's what allows us to replace one program with another if it runs faster and does exactly the same thing. So we couldn't do optimization. The reason we can do optimization is precisely because the meaning function is many to one. So meaning is many to one, and keep in mind, important point here is that it's never one to many. We don't want the opposite situation. If we had the opposite situation where L could map a single point to two different meanings, well, first of all, this would no longer be a function. But also it would mean that the meaning of certain expressions, say in our programming language, was not well defined. That when you wrote a program, it was actually ambiguous whether it meant this or it meant that. And that's a situation we don't like. So we expect our meaning functions to be many to one for non-trivial languages, and we don't want them ever to be one to many. And that concludes today's video. And next time, we're going to go back and continue with our discussion of lexical analysis. Welcome back. In this video, I'm going to show how to use regular expressions to specify different aspects of programming languages. Let's begin with the keywords. And this is a relatively simple case, and I'll just do it for 3 keywords. I'll write a regular expression for if, else, or then, and it'll be obvious how to do it for more. So let's write a regular expression for if, and that would be the regular expression for I, and followed by the regular expression for f. And we're taking the concatenation of these two. And then we're going to union that with the regular expression for else. And what is that? Well, else consists of 4 individual characters, so we have to write out the concatenation of those 4 characters. And as you can see, this is a little bit verbose with all of these quotes and kind of messy to read. So in fact, there's a shorthand that's normally used, and let me switch over to that right now. So if I want to write the regular expression for a sequence of single character expressions, I could just put quotes around the outermost characters in the sequence. So for example, most of the tools will let you write this. I put a quote at the beginning, I write IF, and then I write close quote, and this means exactly the same thing as this. This is the concatenation of 2 single character regular expressions. And similarly for else, and similarly for then. And if I have more keywords, I just write them out and union them all together. Now let's consider a slightly more complicated example. Let's think about how to specify the integers, which we want to be the non-empty strings of digits. So the first problem here is to write out what a digit is, and that's pretty straightforward. A digit is just any of the individual characters 0 through 9, and we already know how to write out single character regular expressions, and it's just a union of 10 of those to specify this, and it'll take me just a moment to finish. There we go. So that's a regular expression for the set of strings corresponding to all the single digits. And because we'll want to refer to this from time to time, and also because that's a very common thing to want to do, most tools have a facility for naming regular expressions. So for example, I can name this one to be digit. So a single digit is anything that is generated or is in the set denoted by this regular expression. And now what we want to do is to have multiple digits. Well, we know a way to do that. We can just iterate a single digit as many times as we like. And so here we get all strings, all possible strings of digits. And this is very, very close to what we wanted, except that the string that we want has to be non-empty. We don't want to count the empty string as an integer. And there's an easy way to do that. We just say that the whole sequence has to begin with a single digit, and then it's followed by 0 or more additional digits. So just to reiterate that, we say there has to be at least one digit, and then it's followed by 0 more additional digits. And this pattern, actually, for a given language, is extremely common. So if I want to say that I have at least one A, I write that as A star, because this says 0 or more A's, the second part says 0 or more A's, and the first part says there has to be at least one A. And because this is so common, there's a shorthand for it. I think is supported by every regular expression processor, and that is to write A plus. And A plus means is just a shorthand for A star. And so we can actually simplify this regular expression a bit and write simply digit plus. Now let's look at yet another example, even more sophisticated than the previous two. Let's think about how to define the identifiers, which are strings of letters or digits that begin with a letter. And so we already know how to do digits, so let's focus on the letters for a moment. So how will we write out a regular expression for the letters? Well, we're going to want to name it, so we'll say that the letters are actually a single letter. And now we have to write a regular expression for all the individual letters. And that's straightforward but tedious. We have to say little a, lowercase b, lowercase c, lowercase d, and well, as you can see, this is going to be rather a large regular expression. We're going to have 26 lowercase letters and 26 uppercase letters, and the whole thing is going to be rather tedious to write down, so let's actually not do that. Instead, let me mention a shorthand that the tools support to make it easier to write out exactly this kind of regular expression, which is called a character range. So inside of square brackets, I can write a range of characters. So how do I do that? Well, I have a starting character and an ending character, and I separate them by a hyphen. And what this means is the union of all the single character regular expressions beginning with the first character and ending with the second character, so everything in between. So this is exactly the regular expression for all the lowercase letters, and then I can have another character range inside the same square brackets for all the uppercase letters, so capital A through capital Z. Okay, and this regular expression here on the right defines exactly the big union that I didn't want to write out. Okay, and that gives us a definition of a single letter. And now we're in great shape. We already have a definition for a digit. Now we have a definition for letter, and so that we can write out the rest of this definition. So we want the whole regular expression to always begin with a letter. Okay, so an identifier always begins with a letter, and after that, it's allowed to be a string of letters or digits. Okay, so the or suggests that there's going to be a union. So after the first letter, we can have either a letter or a digit, and then we can have an arbitrary string of those things. So we put a star on the whole thing, and that is the definition of an identifier. It begins with a single letter, and it's followed by 0 or more letters and digits. Now, because we're doing a complete lexical specification, we also have to deal with even the parts of the string that we're not really interested in. We have to have at least a specification of them so that we can recognize them and throw them away. In particular, we have to be able to recognize the white space. And we're going to just take white space to be a non-empty sequence of blanks, new lines, and tabs, even though there are other kinds of white space characters, things maybe like rub out. Depending on your keyboard, there might be others, but these three will suffice to illustrate all the important points. So, a blank is relatively easy to write down. That's just single quotes around a blank space. But there's a problem with new line and tab, because a new line, a carriage return in the file, has special meaning. Typically, you end the line, you end whatever command you're working on in these regular expression tools, lexical tools. And tab also is not an easy thing to write down, and it doesn't look much different from a blank in a lot of cases. So what tools do is they provide a separate name for these, and typically it's done by having some kind of escape character, and a backslash is the most common one that's used, and then followed by a name for the character. And so backslash n is typically used for new line, and backslash t is typically used for tab. And I just want to stress, the reason for doing this example is to illustrate this, that we have to have a way of naming some characters that don't really have a very nice print representation. There are other characters that that don't even have really any kind of print representation, and we still need a way to talk about them in our regular expressions because they might be embedded in a file that we have to lexically analyze at some point. And so anyway, the way this is done is by providing a separate naming scheme for such unprintable characters. And typically that's done with an escape sequence, so something beginning with a special character like backslash, followed by the name of the character, so N for new line in this case, and T for tab. And so to finish off our definition, this gives us one character white space, and then we want a non-empty sequence of such things, so we wrap the whole union there in parentheses and put a plus on it, and that gives us what we want. Let's pause for a moment in discussing programming languages and look at another example of using regular expressions from a different domain. Here I have an email address, and as it turns out, email addresses form a regular language, and every email processing device in the world, so your mailer and the mail servers that you use, all do regular expression processing to understand what the email address is telling them in the email messages that go by. And so we can think of an email address as consisting of 4 different strings separated by punctuation. There's a username and then 3 parts to the domain. Okay, and let's just assume for simplicity that these strings only consist of letters. In practice, they can consist of other kinds of characters too, but let's just keep things simple. And we can write out the more complicated thing using regular expressions, but the structure will be the same as if we just consider them to be made of letters. And then these 4 strings are separated by punctuation. So there's the @ sign and 2 decimal points that form the separators of the strings. And so this is a relatively straightforward thing to write a regular expression for, given what we know so far. So the username would be a non-empty sequence of letters, and then that would be followed by an @ sign. And then the first part of the domain would also be a non-empty sequence of letters, followed by a dot, and then the rest is just the same. Okay, so here very quite concisely, we have specified a large family of email addresses. As I said, in reality, the email addresses are slightly more complicated, but they can be written out with just a slightly more complicated regular expression. Finally, for our last example, let's look at a fragment of the lexical specification of a real programming language. In this case, that language is Pascal, which is in the Algol family of languages. Pascal is an early example of a typed language, and it's in the same general family as Fortran and C. And this particular fragment of Pascal deals with the definition of numbers. And so let's take a look here. I'll start at the bottom and look at what the overall definition of a number is. So a number consists of 3 things, some digits, and I'll just read out this abbreviation, an optional fraction and an optional exponent. So we're dealing here with floating point numbers. And so a floating point number can have a bunch of digits, and then it can be followed possibly by a fraction or not, and that can be followed possibly by an exponent or not. And the idea, although we can't see it just from this particular definition, is that either the fraction or the exponent can be present independent of the other. So now let's work briefly from the bottom up. Let's just check that digits are what we expect. So a single digit is in fact the union of all the common digits, just as we would hope. And then a non-empty sequence of digits is digit plus. So this is what we've already seen. And now the interesting bit is to look at how the optional fraction and the optional exponent are defined. And the optional fraction looks a little less scary, so let's do that one first. So what's going on inside the fraction? Well, if we have a decimal fraction, there's going to be a decimal point, and that's going to be followed by a string of digits. So this is just the fractional part of the floating point number. It's the stuff that comes after the decimal point. And what's this plus epsilon doing out here? Well, remember, the plus is union, and epsilon stands for the empty string. So what this is saying is that either the fractional portion of the number is present or it's completely absent. So this is how you say something is optional. You write out the regular expression for the thing, and then you do plus epsilon at the end, and that means, well, either everything I said before can be there or nothing is there. Okay? And the optional exponent is structured similarly, but is somewhat more complex. So you can see that the whole exponent is optional because there's some regular expression here that's unioned with epsilon. And so either something is there, and this is the this is the exponent part, or it's not present at all. And now let's look inside how the exponent is defined if it's there. So an exponent always begins with e. So this is exponent, standard exponent notation. And it always has a non-empty string of digits. So there's e followed by some digits, and in between, there's an optional sign. We know the sign is optional because epsilon is one of the possibilities. The whole sign might be absent. And then what are the possibilities for the sign? Well, it could be negative or it could be positive. So either there's a positive or negative sign or no sign, in which case, presumably, it's interpreted to be positive. Now, this idiom, where we have plus epsilon to indicate that something is optional, is also extremely common. And so there's another shorthand that many tools provide. So another way of writing this that's common is to say that that's my fractional component, and then it might be absent. So the question mark after a regular expression just means exactly this construction, that we take that regular expression and we OR it with epsilon. And so this one, this regular expression, is a little more complicated. It has two optional components. So let's just write out what that would look like. So we would have the exponent begins with e, and then we have a sign, which is either plus or minus, and that's optional. So we put a question mark after it, followed by a non-empty string or digits, and then this whole thing is optional. The whole exponent is optional. So this is an alternative and more compact way to write this expression. To wrap up, I hope I've convinced you in this video that regular expressions can describe many useful languages. We've seen some fragments from programming languages, but also we saw that email addresses could be specified this way. Other things that are regular languages are things like phone numbers and file names are also regular. And there are many, many other examples in everyday life where regular languages are used to describe some simple set of strings. And I also want to emphasize that so far we've used regular languages as a language specification. We used it to define the set of strings we're interested in, but we haven't said anything about how to actually implement lexical analysis. We still need an implementation. And that's what we'll talk about in future videos. In particular, we're going to look at the problem of given a string S and a regular expression R, how do we know whether that string is in the language of the regular expression R?
Hello. In this video, I'm going to give a demo of Deducit, a research project at Stanford University for helping students learn formal systems in online classes. The basic idea behind Deducit is to allow students to work through formal derivations and to have their improving technology that will check that those derivations are correct, so that you can actually learn the details of how formal reasoning works. So let's take a look at an example here. So here is a little exercise in algebra, and our goal is to prove that x is equal to 11. All right, that's what we're trying to accomplish. And where we start is with the equation 2 times x plus negative 4 is equal to x plus 7. So in general, there could be more than one initial given assumption. In this particular exercise, there's just one. And we want to start with that equation, and we want to prove that x is equal to 11. And to get there, we're allowed to use any of the rules that are listed here that I'm circling with the mouse. And these rules are divided into two kinds. There are the required rules, which is this first set here at the top. And the required rules are required. So whenever we have a step of our derivation that uses one of these rules, we have to name it explicitly. We have to show that step explicitly. And then there are some rules that are considered free. These are the rules we don't have to show. So for example, we don't have to show all the steps involving associativity of addition and multiplication. Presumably our instructor has decided we already understand that, and we're allowed to skip over those steps, and the system will try to fill them in. So these rules down here, we can show them if we like, but they're not required. We're allowed to skip these steps. All right, so let's begin working on this. And every step of the derivation is going to have 3 parts. it's going to have a conclusion, so something that we are proving at this particular step. Then we're going to have the justification, so the rule from which that step follows. And then finally, what previous facts we're using that we already knew to be true. All right, so what we started with, what rule we applied to it, and then what we concluded from it. All right, so what can we do to make progress in this example? Well, one thing we could do is we could add 4 to both sides of the equation. Okay. And why is that justify? What rule are we using? Well, that's the balance equation using addition rule up here, which says it's okay to add the same thing to both sides of an equation. So we would select that rule out of the list of possible rules. Okay. And then what assumption are we using? Well, there's only one thing that we've got at the moment, and that's the initial given that we began with. All right, so here we have one step of our derivation. We think this is right. We click Update Proof, and the system comes back and says, indeed, yes, that was a valid step of the derivation. Okay, so now let's do another step. Well, actually, let's see what would happen here if we did this balance equation step incorrectly. Let's say we didn't add the same thing to both sides. And so let's try that out. And what do we get? Well, we see that now it comes back colored red, indicating there's something wrong, and we're not given another step here to fill in, okay, because this was an incorrect step. But we also see there's this little question mark icon here, and we can click on that, and it tells us something about what went wrong. It gives us some advice. It says that balancing an equation means you have to add the same value to each side of the equation. Okay, so with that advice, presumably we'll be able to figure out what we did wrong and correct this step and get back to a place where we're on track. Now, I should say that there's not always advice available for every incorrect step, but if it is available, you can click on that and get some idea of what it is you might have done wrong. All right, so now let's go on. Let's take a look at this and see what we could do. Well, we could try to simplify the left-hand side here. So that's equal to 2 times x on the left-hand side. And the right-hand side, x plus 7 plus 4. And we think we can do this here because, 4 plus negative 4, well, that's just adding constants, and that's one of our free rules. Okay, so we're allowed to add up constants, and getting the 0 there should be something we can do for free. All right, and that follows from our previous step. So we select that, and now we can do an update. And it comes back and says, oh, we did something wrong. So this doesn't immediately follow from the previous step. And there's actually a hint here, so we can see why. And we see, oh, so additive identity is a required rule. And so what mistake did we make? Well, it was okay to add 4 and negative 4 together and get 0 and not show that, because that was just adding multiplying constants. But then the subsequent step where we said that 2 times x plus 0 is equal to 2 times x, that is something we're actually required to show in this exercise. So whenever we use additive identity, we have to explicitly say so. So we can fix that by saying that, yes, this step actually follows by additive identity from the previous one. And all the other rules that were used in that step are free, and so we don't have to name them. All right, so now we can go on. We can also simplify the left-hand side. We might as well clean that up. And this is just free rules, so we don't have to say exactly which rule we're using. And I think I didn't hit the update there. Okay, so now, I guess I hit it twice by accident. So let's just get rid of one of these steps. Okay, so now what's the next step we're going to perform? It looks like we need to bring x over to the left-hand side. So we're going to add a negative x to both sides. So I have 2 times x plus negative x is equal to x plus 11 plus negative x. Okay, and that's again the balance equation using addition rule, and that follows from our previous step. Okay, and we can get rid of that one. All right, and when we update that, that works just fine. Okay, and now we can do some simplification on the left-hand side. On the right-hand side. All right, because all of this over here is just equal to 11. Okay, and then we're having to use x plus negative x is equal to 0, and then we're just adding 11 and 0, so that would just count as adding up constants. So this should follow from additive inverse from the previous step. All right, if we update that, yes, that worked out fine. And now we just have to work on the left-hand side. We got 2 times x plus negative x. And in order to get that into a form where we can simplify it, we're going to need to use the distributivity rule. We're going to need to pull out the constants that are in front of the x's. And so we can do that. We can say that 2 plus negative 1 times x is equal to 11. And so we're using distributivity there, but we're also using the unary negation rule that says, negative x is equal to negative 1 times x. But that's a free rule, so we don't have to worry about that. So the only rule we need to name is the distributivity rule, and that follows from the previous step of the derivation. We update that. Okay, and now we're just about there. So now I think in one step we can do the simplification. We can subtract 1 from 2 and get 1, and then we have 1 times x is equal to 11, and that's the multiplicative identity, which is a required rule for this particular exercise. Follows from the previous step, like all the previous steps, and now we're done. And now we've proven x equals 11. The system knows we have finished the assignment. And that is the basic idea behind deduce it. And while this particular example was algebra, this can be done for any kind of formal system where you can present the kinds of exercises you want to do as a set of rules, and the students are supposed to derive some kind of goal using those rules.